All right, welcome to chapter 3 of quadratic functions. We are going to start with 3.1, quadratic functions in vertex form, sketching and transformations. So the first thing that we're going to do is we're going to sketch this. We have two tables of values here and here, and we're going to plot these in according colors. We can see here that we have one that has a little negative right there, and the one on the right is positive. So let's take our first one here. We're going to sketch it. I'm going to sketch it in black. So we have at -2 and -4, we'll have a point. At -1 and 1, we'll have another point. 0, 0, and we can see that it does this neat thing where it looks the same on either side of the axes, and I'm also going to label this. This is my y is equal to -x² graph. I'm going to do my next one here in red. We have another point at -2, +4 this time, so -2, 4, -1, 1, same point at 0, 0, and it does again that little reflect across the axes. Make sure to label. Y is equal to x². Now we have two graphs that look really similar here. The only difference is that it's reflected over the x-axis. And remember that because what it's changing here is our y values are becoming negative or positive. So y is equal to x² is the simplest form of a quadratic function that we will ever deal with. F of x is equal to x² is another way to write the equation. This is function notation. We should remember this from grade 10. The graph shape is called a parabola. There are vertex that is this point right here, kind of the inflection area. It is minimum if it opens up, and it is a maximum if it opens down. And our axis of symmetry is the x value of the vertex. The general form of a quadratic function can be written in two different ways. The first one we're going to deal with is ax minus p squared plus q. This is called vertex form. We'll actually deal with that right away. Or ax squared plus bx plus c. This is called general form. Both have their benefits, both have their downsides. Okay, next page. Now, if we're looking at y is equal to ax², we need to figure out what a is going to do to our graph. We have 4 different charts here. We're going to plot them. We're going to see what happens. Make sure to color code these to see how they look different. A is equal to 1 is our standard graph. So we get to plot that just like how we did the last one. Label it. A is equal to 1. A is equal to 2 will be red for me. It can be any color you want for yourself. So -2. And then 4, 5, 6, 7, 8. This guy comes up. He goes to 2. He stays the same. He comes up and he comes up. Graph. This is A is equal to 2. A is equal to 1/2 will be green for me. So then -2, 2, 1/2, 0, 1/2, 2. Kind of get this little squat looking graph. A is equal to 1/2. And then if you look at A is equal to -2, I'll do that one in blue. We can see that it's going to be like the red graph, just reflected. So that's -2, -3, -4, -5, -6. So let's look at these. Summarize what you see. If A is greater than 0, we know that it's going to open up. If it is less than 0, we know it's going to open down. And we can see that from the red and the blue graph. If A is between 0 and 1, then our graph is going to be wider than our traditional x squared graph. And if it isn't between 0 and 1, so it's greater than 1 or less than 0, so like we're looking at not fractional values. Let's say not fractions, like 1/2. We know it's going to be narrower than x squared, and we can see that from our red one, A is equal to 2, and the blue one. So this one, if we're looking, this is the green, and 4, we're looking at the red. But what about Q? What effect does Q have on the quadratic function y is equal to x squared plus Q? So let's graph this and we'll see what happens. Q is equal to 0. This is our standard one that we're looking at, so I'm going to graph that one in black. Always make sure to label. Q is equal to 0. Q is equal to 3. We have x squared plus 3. I'm going to put that one in red. So if I go to x is -2, and then it's going to go to 7. So instead of at 4, it's going to be 5, 6, 7. So we can see that dot move upwards by 3. -1 goes to 4. So 1, 2, 3, 4. Again, upwards, upwards, and upwards. So I think you can already see what effect Q will have on the graph, but let's confirm with a negative value one. Q is equal to -2. So then if I'm looking at -2, I'm only going to go up to 2 this time. If I'm at -1, I'm actually going to be at -1. My 0, my vertex point, will drop down to -2, up and up. Q is equal to -2. So what does the value of Q do? The value of Q moves our graphs up and down. If Q is greater than 0, the graph will go up. And if it is less than 0, it will go down. Next page. What value does P have on the quadratic function? X minus P squared. So this is that vertex form that we're looking at. And what is it going to do is the real question. So let's graph our original. Done and done. P is equal to 0. If P is equal to 2, let's graph that in red. At -2, our value will be 16. That's kind of big. I'm not going to move that one around. At -1, that's a valuable point. So -1, and then we go up to 9. So -1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 0 to 4 and that's weird. Give me a second. If I plug in -2 to that, yeah, that's 16. -1 into that. 9. And then 1 into that. Yeah, okay. We're good. So then 1, 1 should be right here. 2, 0 right here. 3, 1. 4, 4, and 5, 9. Here we go. I see what I was doing. P is equal to 2. So we can see that these points shifted somehow enough to confuse me partway through, but that's fine. So let's count out this one. P is equal to -3 in blue, sorry. So 1, 2, 3, 4, 5, 6, and 9, 5, and 4. So 1, 2, 3, 4, -4 and 1, -3 and 0, 2 and 1, -1 and 4, and our new y-intercept at 9.
Candace, could you please take line 1?
So in using this, we can see from our black graph that we are looking at shifting this way by -3 and shifting this way by +2. Now what we can see here, I want to draw our attention to this is really y is equal to x minus 2 squared, but our p-value is flipped. It's the same thing for when we look at y is equal to x plus 3 squared. When we remember our transformations, we should always remember that our x values get a flip and our y values stay the same. So the value of p does what? It shifts our graph left-right. If p is greater than 0, so if it's x minus p squared, it'll be p units right. And if it's x plus p squared, it'll be p units left. Okay. Next page. We need to learn how to find the vertex, domain, range, and axis of symmetry from vertex form. So if we're looking at 2 multiplied by x plus 6 squared minus 3, let's write this out. So f of x is equal to 2x plus 6 squared minus 3. This is p. This is q. So remember I said p-value must always, always, always be flipped. So if we're looking at this, we can call it really -p, q. So then this will be -6 bracket -3 is our vertex. Our domain and range of parabolic graphs, domain will always be x, e, r. X is an element of all the real numbers. Range will depend on whether or not this graph is opening upwards or downwards. Now, I can tell that this graph opens upwards, and I'll explain how later. So I know that y must be greater than or equal to the q value of my graph, but it must also be an element of the real numbers. Our direction of opening depends on our a value. So when we look at this, and I have y is equal to ax plus p squared plus q, this guy, in our case, is 2. He is positive. So this means he opens up. And we have a min value at y is equal to -3. Our axis of symmetry, this is the p value in vertex. So that means x is equal to -6. And our intercepts. So let us find our y-intercept by plugging in 0 for x. So f at 0 is equal to 2, 0 plus 6 squared minus 3. So 2 multiplied by 36 minus 3 is equal to 72 minus 3 is equal to 69. Well, unfortunately, that number is not very useful, so let's start that. And it's not useful in the regard that it is not easy to plot. So how are we going to find more points? Because if I start plotting this, what we can see is that I have vertex at -6. So 1, 2, 3, 4, 5, 6. 1, 2, 3 right here. And I know I have my axis of symmetry. I'm going to plot that in red. Please always plot your axis of symmetry and label it such that x is equal to it. It becomes more relevant the farther we go in pre-calculus, so it's a good habit to start now. Now, we know that we need at least 3 points to plot a graph. We know that when we were looking at the original graph, that if we had 1 point, it reflected over this axis of symmetry, which means that it's more than possible for us to find that. So what I'm going to do, and it is a skill that we'll use down the road as well, is we're going to test points. Test point, axis of symmetry. So A, O, X. Now the point I'm going to use is going to be the one to the right of the axis of symmetry. So X is equal to -5. You could choose any number as long as it's to the right or to the left. We only need to do one because we're using the axis of symmetry. So it is very useful in that regard. So scroll down. We are testing f at -5 is equal to 2 bracket -5 plus 6 squared minus 3 is equal to 2. 1 squared minus 3 is equal to 2 minus 3 is equal to -1. So that means I have a point at -5, -1. So let's plot that. -5, -1. And then using the axis of symmetry, we want 1 over, 1 over. We should have a point at -7, 1. Because we have 1 unit to go to hit the axis of symmetry. We have 1 more unit to go to get to the next point. We can plot this. And it doesn't need to be any more accurate than that right now. When we have more tools of the trade, it can be more accurate, but for right now, it's okay. So let's look at this. We need to do a your turn. I want you to pause the video here. I want you to try and do this on your own. When you come back, I will have the answer up for you. So our vertex here is -1, 3. Remember to flip the p-value. The domain is such that x is an element of the real numbers range. We can see that it is going to open down because of the a value, so we know y must be less than or equal to -3, such that y is an element of the real numbers. Direction of opening, like I said, it's down. And there's a max at y is equal to -3. At +3, sorry. Lots of positives. Our axis of symmetry, x is equal to -1. And our intercepts, if we are looking for our y-intercept, always check that one because it tends to be the most useful or not. It's kind of in between. So y is equal to -3. 0 plus 1 squared plus 3 is equal to -3 multiplied by 1 plus 3 is equal to -3 plus 3 is equal to 0. That might be really useful for us. Okay, let's plot. So we know our axis of symmetry is at -1, 1, 2, 3. We have 0, and then our axis of symmetry is at -1, like I said. I'm going to plot that in a nice red line. X is equal to -1. Using my axis of symmetry, I can plot another point here and graph. Done and done. We have a nice little summary for you guys to follow. This should help you as you go. If you have any questions, make sure to do it, go through it. I'll check anything on there. That will focus specifically on transformations. The next one we're going to do here is we're going to do reading graphs and modeling problems. This is a slightly different section, but not really, so we're going to keep it together in the 3.1 section. So if I'm looking at this graph and I want to determine a quadratic function in vertex form for each graph, first thing I should find my vertex. So the vertex here is 5, -4. Now, here's what I'm going to do. I'm just going to write down my vertex form, and then I'm going to plug in what I know. And it's not a lot, and that's fine. Now, I notice I have 2 clear defined points on this graph. Really, the key to creating a vertex form equation is making sure that we have our a value. The only way we're going to be able to find our a value is if we plug in something for our x and y. So I'm going to use this point here because that point is a little bit easier. So then -1 is equal to a 2 minus 5 squared minus 4. So -1 is equal to a 9 minus 4. We're going to add 4 over to both sides, so we get 3 is equal to 9a. And then you should get 1/3 is equal to a. So, therefore, we have a function, f of x is equal to 1/3 x minus 5 squared minus 4. Okay, I want you to try the second one on your own. Pause the video, give yourself some time to work through it. And I'm going to work through the solution here. When we look at this, we can see that our vertex is 0, 3, which is awesome. It's going to make things a lot easier. The point I'm going to declare right now, I want to use 1, 1, which is also an awesome point. Makes life really easy. So then y is equal to ax minus 0 squared plus 3. Plug in your point now. 1 is equal to a x squared. Oh, sorry. Jumped ahead there a little bit. Is equal to 1 minus 0 squared plus 3. 1 is equal to a plus 3. So then we get -2 is equal to a. Therefore, the function is equal to -2 x squared plus 3 because we don't write unnecessary zeros, and to further it, we don't write unnecessary brackets either. And that should be the final answer. We're going to do a quick modeling problem, and then there will be the last bit of the assignment available for you guys. So suppose there's a parabolic archway, right, that has a width of 280 centimeters and a height of 216 centimeters at its highest point above the floor. Write a quadratic function in vertex form that models the shape of this archway. Well, what we can see here is we have a couple different points actually in this thing. We have a point here, a point here, and a point here. We're a little unsure of some of these. We know for sure that this one's 0, 0. We know for sure that this one is 280, 0, because it is 0 above the floor. This is where we start. This is where we end. This is the halfway point. So this point is going to be 140, 2/16. This is the only thing that's indicative of what height we have. So this is our vertex as well. When we look at this, let's plug in some values. F of x is equal to ax minus p squared plus q. Let's plug in this point because it is the easiest point, and we'll plug in our vertex at the same time. So 0 is equal to 0 minus 140 squared plus 216. So then we should get negative 216, because we're going to jump this guy over, is equal to 19,600 and we're going to leave this in fractional form when we divide over, so it'll be negative 27 over 2,450 is equal to a, and then you would finish that up, make sure that you write out the equation, remembering that that is the a value. And I'm not writing it because I'm writing it right away for b. So if I need to determine the height of the archway at a point that is 50 centimeters from its outer edge, I'm trying to find the height, so I know the function will be at 50, writing it in function notation, is equal to negative 27 over 2,450 multiplied by 50 minus 140 squared plus 216. I also want to draw the fact that it makes sense that our a value is negative because this archway should be opening downwards. So always make sure to take a second to see if your answer makes sense. So negative 27 over 2,450 bracket 8,100 plus 216 should leave us with an approximate value of 126.7 centimeters. Everything else in the question is to the nearest whole value. Therefore, we will also go to the nearest whole value, 127 centimeters. All right, you can see in the bottom right here, we have the assignments. Make sure to do this assignment and the assignment on the last page. And if you have any questions, please let me know.